everyone, thank you so much for watching. Today we'll be doing a video ahead of midterm 2. The very first problem will be, the very first two problems we'll be dealing with are problems of continuity of piecewise functions. So if we actually take a look at this problem, that's actually from worksheet 3, which we would have done had it not been for midterm 1. So that's just the topic that's relevant from that worksheet is continuity of piecewise functions. So for each function, we're supposed to find all values of k for which the given function is continuous everywhere. If no such values of k exist, we need to state this and explain. So if we actually take a look at this function in part A, it's a piecewise function. The top branch is what applies if we plug in x less than or equal to 2. So anything 2 or under gets k times x squared as the formula. And anything above a 2 for the bottom piece, that's going to be x plus k. Now we want to make this function continuous everywhere, meaning for all values of x. So this function is clearly defined for all values of x. So if we actually take a look at this and we, I'm getting the stylus ready. So if we actually take a look at this function and we actually draw this axis of numbers, the border point, the point that touches both conditions, the point that's actually in common to both, is going to be the x equals 2 point. Now, clearly, each piece is continuous in its own right. The k times x squared, that is actually continuous on its own. It's a parabola. It's a quadratic function. Nothing gets nicer in terms of continuity. It's continuous, it's smooth, everything is nice. The bottom piece, x plus k right here, that's actually a line. So lines are also continuous. You can draw a line without lifting your pencil off the paper. The only possible point of friction where we have to do work and choose k sensibly to make it continuous is the point x equals 2. So what we want to do is we want to make sure this function is continuous at x equals 2. To that effect, we have two branches here. We have what goes on to the left of 2 and to the right of 2. So this is what you would call x is less than or equal to 2. That's to the left of 2. And the region to the right, that's going to be the right of 2. That's literally greater than 2. So for this one, the one to the left, it's Roman numeral 1, that's the top branch. And Roman numeral 2, this one is going to be this right branch, this one. Okay, now let's actually state this formally. So each branch slash piece is continuous in its own right. It just remains to make sure that f of x is continuous at x equals 2. Parentheses, the border point. Basically the point that touches the two branches, which we have circled up here. Good. So, how do we ensure that? Using the definition of continuity, so a function or f of x, so the definition of continuity is f of 2 exactly at 2 is equal to limit as x approaches 2 of f of x. So the function very near that point, as in the limit, has to actually agree with the function at that point, f of 2 exactly, when we actually plug that in exactly. So let's actually see how we can make that happen. For the limit x approaches 2 f of x to actually exist, we need the two one-sided limits to be equal. In other words, left equals right. Good. Now let's take a look As in, if you look at this axis of numbers, the left of the point 2 is what's labeled clearly left, that's less than 2, and what's to the right is greater than 2. So actually, let me actually do the limits. So limit as x approaches 2 minus, that's not 2 to the power of minus, let me remind you. That's read 2 from the left. That means x approaches 2 from the left, as in a bit to the left of 2 of f of x. So think of it as plugging in something like 1.99 for x. So x is like something 1.99. In which case, what branch will we use? We will use the top branch, Roman numeral 1. That's the left. Because if x is equal to 1.99, then it's a bit less than 2, so that falls under the jurisdiction of this one. X is less than or equal to 2. So in this case, we have the formula, limit as x approaches 2 minus, what is that going to be? It's going to be the top formula, kx squared. So that's going to be k times 2 squared, and that's going to be 4k. Okay, that is indeed the left. Now let's take a look at the right. Limit as x approaches 2 plus f of x. What does that mean? It means something like x is something like 2.01, a bit greater than 2, but slightly close to it. So that's going to be the right limit. That's going to fall under the category of Roman numeral 2. Because if x is 2.01, then it's greater than 2. So that's going to be the formula x plus k, this formula right here. So x plus k. So it's going to be limit as x approaches 2 plus of x plus k. And that's going to be what? 2 plus k. I'm literally plugging in place of x, not k. K is still a variable, k is still an unknown that we need to figure out. The variable that I am plugging into is x. Notice the limit says x. X approaches something, so I need to do that. X approaches something. Good. So in this case, I got 2 plus k. That's going to be the right. So for left to be equal to right, which is what we actually want with continuity, we need 4k equals 2 plus k. Subtract k for both sides and to be able to solve this high school algebra equation for k. So that's going to be 3k equals 2. Divide by 3, and what do you get? K equals 2/3. That seems like a good final answer. And that is indeed the only value of k that makes the left equals the right. Now, people will inevitably ask, what about f of 2? We need to make sure that left and right are equal, which we have already done. But looking at this definition, we also need to make sure that we do f of 2 exactly is equal to the left and right. The point here is that we don't need to worry about f of 2 exactly. If you'll take a look at the top branch, Roman numeral 1, it says x is less than or equal to 2. So that branch takes care of the left, meaning something like 1.99 less than 2, and it also takes care of 2 exactly. So they do overlap in that sense. X equals 2 exactly falls under the category of Roman numeral 1, and to the left, x equals 1.99, that also falls under said category. So the only thing we have to worry about now, we had to worry about was left equals right, in which case k equals 2/3 is exactly what gets us to where we want to be. That's it for this problem. Okay, now we'll be doing the next and final problem on continuity. The same instructions as the last problem. You want to make sure this function is continuous everywhere, which each branch, as you can see, is continuous in its own right. So that basically gets copied over as is. And the only point of possible friction we have to worry about is making it continuous at x equals 2. So literally the same instructions, but a different function. So I am now going to copy the things we have actually written down for this problem for efficiency from the previous part. So let me actually copy this stuff. Literally the same objective, same rationale. Let me just copy this over. So basically, it's literally the same point of contention, x equals 2, and you want to try your best to choose k so that the function is continuous at x equals 2. So each branch or piece is still continuous in its own right. The top one is a parabola, something like k squared times x squared, so that's as nice as it gets, still continuous. 8k minus 4x with the bottom branch, let's also label them Roman numeral 1 and Roman numeral 2 for top and bottom. That's good. So the top one is still going to be a parabola. The bottom one is still going to be a line. Good. Now, what do we have to do now is to make sure that the function is continuous at 2. Why? Because each branch is continuous in its own right. The only point we have to worry about now is the point x equals 2. That's the point where it's continuous. So you want to make the limit to the left equals to the limit to the right, like we have stated. Remember, the top branch says x is less than or equal to 2. So that includes the 2 exactly. So the only thing left for us to worry about is limit of left equals limit to the left equals limit to the right. Okay, well, let's take a look. Limit x approaches 2 minus, that means limit x approaches 2 from the left, so x is something like 1.99. That falls under the category, let me write the function name f of x. I believe it's f of x, very good. So now for this one, you got to do limit as x approaches 2 minus. Which formula are we going to use? If x approaches 2 minus, it's going to be a bit to the left. So 1.99 is the x. So let's just do k squared times x squared. So that's going to be k squared times 2 squared, and that's going to be 4k squared. That's, I believe, the left. Limit as x approaches 2 plus, f of x is going to be what? Limit as x approaches 2 plus. Which formula are we going to use for the right limit? When we say x approaches 2 plus right here, just a reminder, this means a one-sided limit. It does not mean 2 to the power of a plus. That would be meaningless. In this case, what I'm saying is x approaches 2, but from the right, meaning something that's very close to 2 in x, but a bit greater than. So that's x is approaching, so basically x is something like 2.01. Which branch handles the case x equals 2.01? I believe it's the bottom branch. So that's going to be 8k minus 4x. So let's actually plug that in with the x. Remember, it's x that does the approaching job. It's not k. K is an unknown that we have yet to resolve. So we plug the x approaches into the x, not k. So 8k minus 4 times 2. So that's going to be 8k minus 8. And that is going to be the right. Good. Now, to make it continuous, we got to make left equals right. So to ensure continuity, we want left equals right. So we have 4k squared is equal to what now? 8k minus 8. We still need to see if we can solve this little equation for k. One thing we can and potentially should do is divide both sides by 4 to clean up this little monstrosity. So we get k squared is equal to what? 2k minus 2. Good. Now, move this 2k to the right. Take out 2k minus on both sides. K squared minus 2k is equal to negative 2. Now add 2 to both sides to get rid of the negative 2 on the right. And you get k squared minus 2k plus 2 is equal to 0. This is what you would call a quadratic equation in k. How do we actually solve this quadratic equation for k? We can either use the quad formula or use the shortcut for lovely numbers, which in this case, the shortcut is not at all obvious. So it won't be a nice factorization with clean integers. So let's try to solve. So use the quad formula. Use the quadratic formula. For k. Okay, so how do we do that? K is equal to... this is just literally me plugging into the quad formula. So minus 2 makes plus 2. Plus or minus negative 2 squared minus 4 times 1 times 2. Again, if the quad formula is something you don't remember, you might want to look into it or potentially put it on your cheat sheet because it's always useful. Divided by 2 times 1. Let's expand. 2 plus or minus 4 minus 8. And that is divided by 2. That's equal to 2 plus or minus square root of negative 4 divided by 2. Okay, well, we have this unfortunate situation where we have the square root of a negative number. Like we said, the second rule of the three cardinal rules of domains of definition in this class is thou shalt not take the square root of a negative number. Square root of negative 4 is not a real number. It's outside the scope of this class. Conclusion, there is no such k. We tried to solve for k, and we ended up with a k that looks like the square root of a negative number. So no such k exists that makes the function, or makes f of x, plain f of x, continuous at x equals 2, which is a perfectly legitimate answer. If you actually do this, if you actually take a look at what happens with if you actually take a look at the instructions, it says find all values of k for which the given function is continuous. If no such values of k exist, state this and explain. Well, we have correctly stated that no such values of k exist for part B of our problem, and indeed, we have the explanation. The explanation is in the quadratic formula. The quad formula gives you the square root of a negative number, ergo there is no such k as per the rules of this class. And that's it for continuity. Okay, everyone, now we've come to the portion of the video that deals with derivatives. We're past continuity. So for problem 1, this is now worksheet 4, by the way. So we're done with worksheet 3. The only part of it that was relevant for the video was the continuity. So for this one, it's problem 1, part D. Compute the derivative of each function below. F of x is equal to 11 over x to the 6th minus 3 over x to the 4th plus minus 2 divided by x to the 3rd plus 8 over x. Now, this is basically what you would call a power rule problem, so you definitely want to make sure that you use the power rule, which is the most convenient of all the rules of derivatives. Definitely don't want to waste the quotient rule, which is the most cumbersome, on each of these 4 little fractions, because the quotient rule is the most tedious, and we're only going to use it when we absolutely have to. There are situations where you have to use it, but this is not one of them. We just want to rewrite the function to bring out the powers that are hiding. Just to remind you that reciprocals are nothing but powers in disguise. So I believe f of x can be written as 11 times x to the negative 6 minus 3 times x to the negative 4 minus 2 times x to the negative 3 and plus 8 times x to the negative 1. That's over and done with. So let's actually apply the power rule here. So using the power rule on each power, f prime of x is equal to 11 times negative 6. I'm literally taking this little guy, yanking the negative 6 and migrating it to the front, times x to the power of negative 6 minus 1. Next one is this one, negative 3 as is, times negative 4 times x to the power of negative 4 minus 1. Next one is negative 2 as is. Just copying on the, maybe I should have continued on the same line. I'll just zoom out a bit. Sorry about the lack of the over zooming on my part. So this one is negative 2 times negative 3 times x to the power of negative 3 minus 1 plus 8 times negative 1 times x to the power of minus 1 minus 1. Let's actually try to clean up the numbers a wee bit. So f prime of x is going to be equal to, this one is 11 times negative 6 is negative 66 times x to the power of negative 7. Minus 3 times negative 4 is plus 12, x to the power of negative 5. Minus 2 times negative 3 is what? Plus 6, x to the power of negative 4. And 8 times negative 1 makes negative 8, so negative 8, x to the power of negative 2. This is a perfectly legitimate correct final answer. If you want to bring this back into the form of fractions, which some of you would like, you can also do that. But insofar as computing a derivative, this is a perfectly legitimate final answer which we can put in a box. Okay, this is now problem 2 of worksheet 4. Find the equation of the tangent line to each of the functions below at the given point. The function is f of x is equal to 2x squared plus 2x plus 6 at x equals 1. Okay, now let me remind you the equation of the tangent line, pretty much any line in point slope form of the tangent line, can be written as y minus y sub 0 is equal to m times x minus x sub 0. Good. Now, the x sub 0 and the y sub 0 is nothing but the tangent point. The tangent point. X sub 0 has already been dictated to us. We said what follows the word at. In this case, it's at that gives it away. So at that point, x equals 1. So the x sub 0 equals 1. That is indeed the tangent x coordinate. How do we find the y sub 0? Y sub 0 is equal to f of x sub 0, which is f of 1. How do we find that? Let's plug into the function. So f of 1 is equal to 2 times 1 squared plus 2 times 1 plus 6. That is going to be what? 2 plus 2 plus 6. That's 4 plus 6, and that's 10. So we now have the y sub 0 is equal to 10. Let's just write this on a new line. We have the x sub 0 and we have the y sub 0. The equation of the tangent line is kind of a three-part fill-in-the-blank problem. You got to find this, which has been taken care of. You got to find this, which has been taken care of. And now the only thing that remains is m, which is the slope. The slope of the tangent is nothing but the derivative evaluated at that tangent point. So the slope of the tangent, when I say tangent, I mean tangent line. This is different from the tangent trig function. So there are two different concepts. So the slope of the tangent line can be computed, or should be computed, using the derivative. So let's compute the derivative first and then plug in. First, you find the formula, and then you plug in into math. You never plug in the variable first and derive second. You derive first and then plug in the variable. So what's the derivative? 2 times x. Just power rule, literally using the power rule. Plus 2, a clean 2, the slope. So that's going to be 4x plus 2. Good. Now f prime of 1... because remember, the x sub 0, let me actually highlight that. The f prime of x sub 0, which x sub 0 is 1. So f prime of 1 is going to be what? 4 times 1 plus 2. I believe that's a 4 plus 2, which is a 6. That is the m. That is the m. That's the slope. M stands for slope. M is 6. Good. Now all we got to do is literally plug in the 3 double underlined pieces of the puzzle into the equation of the tangent line. So now this doesn't become a question mark. This basically becomes a check because we have found it. Just a nice little check mark, just for our own bookkeeping purposes. So y minus 10 is equal to 6 times x minus 1, which is a very good answer to put in a box. Some people might want to simplify that and basically migrate the negative 10 to the other side. That's not necessary. On an exam, the instructions didn't say find the equation of the tangent line in a specific form. In this case, we're free to use either form. You can either use this, which is point slope form, or alternatively, you can also manipulate this and bring out the slope intercept form that's hiding in disguise. Either form would be fine. I believe this is a wee bit easier, so that's why I'm leaving it as is on the video. Okay then. Problem 4, same worksheet number 4. Compute the derivative of each function below. We're going to be doing this one. F of x equals x cubed minus 1 in parentheses times square root of x plus 4 in parentheses. Let's actually rewrite this because derivatives like powers. They don't like reciprocals and they don't like roots. So let's rewrite this. Literally, just me rewriting the square root as a power of 1/2. That's something you definitely want to know. So square root of x is equal to x to the power of 1/2. Good. Now, how do we actually compute this? Well, in this case, we got a product, because like right here we can see a product. This is a product of two functions. So we might as well use the product rule. So we can use the product rule. F prime of x, let me remind you of what the product rule actually says. Take the function as is, the product that is the function that is defining the function, and then add to it another copy of the product. That's if you want to remember it. You can also put it on your cheat sheet, the product rule. For the first product, the apostrophe goes on the left term in the product, and the apostrophe goes on the right in the right product. That's pretty easy enough to remember as kind of a mnemonic. So f prime of x is, let's see, how do we actually compute this? Well, what's the derivative of the apostrophe, this little guy? What's the derivative of x cubed? It's nothing but 3x squared. 3x, 3 minus 1, power rule. Minus 1, what's the derivative of negative 1, which is a constant number that doesn't have an x in it? It's 0. So we might as well leave it like that. Times x to the power of 1/2 plus 4. Good. Plus x cubed minus 1. What is the derivative of this? Let's compute this prime. It's going to be the derivative of plain x squared, so it's 1/2 times x to the power of 1/2 minus 1. What's the derivative of the plus 4, which is just a constant number that doesn't have an x involved in it? It's just 0, so we might as well leave it like that. Let's clean it up a bit, within reason, of course. So f prime of x is equal to 3x squared times x to the power of 1/2 plus 4 plus x cubed minus 1 times 1/2 to the power, times x to the power of negative 1/2. Okay, this seems sensible enough. So let's actually distribute the parentheses now. F prime of x is equal to 3x squared, x to the power of 2 plus 1/2, plus 3 times 4 times x to the power of 2, plus 1/2 x to the power of 3 minus 1/2, minus 1/2 x to the power of negative 1/2. Okay, we can clean this up a wee bit. So f prime of x is equal to 3x to the power of 5/2, because 2 plus 1/2 is 5/2, plus 12x squared plus 1/2 x to the power of, this little guy is the same as 5/2. 3 minus half is 5/2, minus 1/2 x to the power of negative 1/2. Good. Now, the only thing we can do is consolidate like powers of x. The only two powers of x that are identical in power or exponent are these two. So you basically have f prime of x is equal to 3 plus 1/2 makes 3.5, which is 7/2, x to the power of 5/2. Those are over with. Plus 12x squared, over and done with. Minus 1/2 x to the power of negative 1/2. Over and done with. This seems like a very legitimate, beautiful final answer to put in a box. Okay. Everyone, now comes the problem 5 of worksheet 4. Compute the derivative of each function below. Now, each function below, in this case, the function b in part b is a quotient, and there is no obvious shortcut to take to avoid the quotient rule, so we have no choice but to use the quotient rule. So, use quotient rule. Use the quotient rule. It's not like one of those ones we did in class where we could do a clever algebra shortcut to reduce it to a bunch of smaller fractions. This is one big denominator and one small numerator, so that little fact splitting along the numerator trick doesn't work. So it's inevitable that we're going to have to use the quotient rule. So f prime of x is going to be equal to what? Let's actually see this. It's going to be what I recommend with the quotient rule, kind of like a mnemonic to remember it or avoid using mistakes, is literally take numerator times denominator minus numerator times denominator, divide by denominator squared. Good. Now, the only thing we got to worry about now is putting the apostrophes, the primes, in the numerator. First one gets the left one, like in the product rule, and this one, that's not a 1, by the way. Sorry about the awkward penmanship. That's going to be x prime. And this one is going to be, the prime is going to be attached to the left guy with the one in front of the minus sign. So, with a minus sign in front of it, rather. So, in this case, let's actually compute each of these and see what we get. We get, look at this, x prime. What's the derivative of a plane x? We have already said it's just 1. 1 times x squared plus 11x plus 9. Good. Minus x times, what is the derivative of this little guy, this big guy in parentheses, where all of it gets a derivative? Well, we can use the power rule on each building block. What's the derivative of this x squared? It's 2x. What's the derivative of plus 11x? It's plus 11. That's just the slope, the thing that's actually multiplying the x. And what's the derivative of the plus 9? It's 0. So plus 0, and that is divided by the big, scary-looking denominator squared. Lovely. Now, in this case, we can and should clean up the numerator a bit. No one would expect us to clean up the denominator on an exam when the denominator is so big and we want to square it. So for the numerator on top, we can and should distribute the parentheses just a wee bit. So 1 times this one. 1 times anything is going to stay the same. So might as well just copy over what's inside the first pair of parentheses. Minus, let's distribute here, negative 2x squared minus 11x. And when you have a 0, well, we might as well cancel the 0. 0 times anything. 0 doesn't actually contribute anything, so that's no problem at all. So let's actually see what we have here. Divided by that big, ugly-looking thing squared. Not that it's a problem that it's ugly, it's just cumbersome. Okay, let's clean up the numerator a bit. X squared minus 2x squared. This one and this one go away, so you're left with negative x squared. And then you have plus 11x, that I believe is a plus 11x, minus 11x. So these two just cancel and go away. And then you have plus 9. So you have plus 9 divided by x squared plus 11x plus 9 squared. And that's a good answer to put in a box. Let's move on to the next part that I'm solving. Not part B, but I believe the last one was part B. Now this is part D of problem 5 on worksheet 4. This one is also a quotient rule problem. Like I said, the big, in this case, it's not a humongous numerator divided by a measly denominator that we can just split into tinier fractions. So in this case, there is no clever algebra workaround, and you're going to have to use the quotient rule. So in this case, let's actually use the quotient rule. So use the quotient rule. So f prime of x, what I'm going to do is, f prime of x is going to be, let me actually write this down with that mnemonic that I've set up. First of all, write the subtraction of products on top. Numerator, not minus negative 2 times negative 2x plus 5, minus 3x minus 11 times negative 2x plus 5, and that is divided by negative 2x plus 5 squared. Now, you put the apostrophes on top. The first apostrophe goes on the left in the left product, and the apostrophe on the right product goes on the right, unsurprisingly. Now let's clean up the primes and see what we get. So f prime of x is going to be equal to, okay, so first one is the prime. What's the derivative of 3x minus 11? That's a line, and the derivative is the slope. What's the slope of the line? It's literally what multiplies the x. So in this case, in the case of this apostrophe on the parentheses, it's going to be 3. So it's going to be 3 times negative 2x plus 5, good, minus 3x minus 11. Now, what did we do with this case? This is also a line, so we can take the shortcut. What's the derivative of this case? It's negative 2x plus 5 is a line, so the slope, the derivative, after all, is the purpose of that is to measure the slope in part. So the slope is the number that multiplies the x, so it's negative 2. And that is divided by negative 2x plus 5 to the power of 2. Good. Now, we can and should clean up the numerator just a wee bit because we have a bunch of numbers in parentheses. Let's see what we can clean up. 3, in this case, in the pair of this case of the first pair of parentheses, negative 6x plus 15 And in this case, it's going to be negative 2 times negative. In this case, it's going to be a plus 2. So it's plus 2 times 3x minus 11. And that is divided by negative 2x plus 5, all of that squared. So in this case, it's f prime of x negative 6x plus 15, rats. Now, let's distribute the parentheses. 2 times 3x is going to be plus 6x. Plus 2 times negative 11, that's going to be negative 22, divided by negative 2x plus 5, all of that squared. Now, the negative 6x and the 6x in the numerator, they cancel. 15 minus 22 makes minus 7, negative 7. So the final answer is going to be negative 7 divided by negative 2x plus 5 squared. And that's over and done with. That's a good answer to put in a box. Okay, everyone, now comes the turn of problem 7a. Compute the derivative of each function below. So let's actually see what we can do. F of x equals the cube root of x squared plus 2x plus 5. So as you'll recall, derivatives like powers. They do not like roots. That's what we want to see when we do derivatives. We want to see powers. So in this case we might as well write the cube root. So cube root might as well be called power of 1/3. So in this case, f of x might as well be written as x squared plus 2x plus 5, all of that to the power of 1/3. Okay. So what do we do now? This is what you would call a generalized power rule. So this is a generalized power. Let me write that down. Generalized power. What do I mean by this? I mean that we don't have a pure power, a pure x to a power third. We have a function, a more complicated expression of x's involving x's to the power of 1/3. So the generalized power rule says the following. What we got to do is f prime of x is equal to, basically this is the general, what you might see it in other authors' works. You can see this as chain rule plus power rule. Chain rule plus power. Good. F prime of x is going to be literally me applying the power rule on the outer part. Take the 1/3 that's right here and yank it out to the front. 1/3 times x squared plus 2x plus 5, all to the power of 1/3 minus 1. We shave 1 off the power. And then you multiply by the derivative of the inner part. What's the derivative of the inner part? X squared plus 2x plus 5 prime. Literally, take the derivative of the outer part with the product rule and multiply by the derivative of what's inside the power with how we usually do it. The only thing left is to compute this little guy. Okay, so f prime of x is equal to 1/3 times x squared plus 2x plus 5 to the power of, what's 1/3 minus 1 right here? It's negative 2/3. And that is multiplied by the derivative of the inner part. What is this derivative actually? The whole prime. That's going to be x squared prime. That's going to be 2x, power rule, plus 2x. The derivative of that is just going to be the plus 2, the coefficient, because it's the slope, and the slope multiplying x is plus 2 in this case, so plus 2. And the derivative of the 5 doesn't actually contribute anything because it's a number. It's a 0. So that seems like a good final answer to put in a box. This is what you would call a chain rule plus power rule, or a generalized power rule problem, however you prefer to call it. As opposed to a clean x to a clean power, x to the power of 1/3, we now have a function of x, the x squared plus 2x plus 5 right here, to a power of 1/3. So we need to account for the fact that the inner thing has a derivative. Now, compute the derivative of each of the functions below. In this case, it's e to the x divided by x squared. We don't, in this case, actually have a shortcut because it's not a power of x divided by a power of x. It's an exponential e to the x divided by x squared. So there is no better option than to use the quotient rule here. F prime of x is going to be the following. Literally, just me plugging into the quotient rule. E to the x prime, numerator prime times denominator, minus e to the x times x squared prime. That's divided by x squared squared. Okay, let's actually start cleaning up and writing the junk that's hiding with the primes. So what's e to the x prime? This one, what's that? That's e to the x. Remember, when you derive e to the x, you get e to the x as is, multiplied by x squared. Minus e to the x, multiplied by what? What is this one? That is the derivative of x squared, that's just 2x. Power rule. Divided by, remember, let me remind you that this one, this little guy, is e to the, a power of a power, so we multiply powers. So it's x to the power of 2 times 2, which is x to the 4th. Now, one thing we can and should do is we can factor out the common factor of x on top. So we have e to the x. We can factor that out because this is common. And we can also factor out a clean x factor, so times x. For the first one, it's going to be x, because x times x is x squared. That's accounting for this little thing. And minus, this guy is 2x. This guy is 2x, so minus 2. And that is divided by x to the 4th. Now, what can we do? We can take this x and we can take this x and cancel by subtracting powers, and we get x to the power of 4 minus 1. Literally just me subtracting powers. F prime of x is equal to e to the x times x minus 2 divided by x to the 3rd. And that seems like a good final answer, in the most simplified form possible. Again, it's good that we did that simplification. It's good if, in case, for the future, when we do applications of derivatives, you'll see that you want to plug stuff into your derivative formula. So in this case, it's good to actually be able to do that. last but not least comes the problem 9, the problem focusing on ln's, or logarithmic derivatives. So compute the derivative of each of the functions below. In this case, it's part C. F of x is equal to ln of x divided by e to the x. There is no better alternative than using the quotient rule here, because it is a quotient and it's not something hiding in disguise. It's a log divided by an exponential. There is no powers to clean up or reduce the fraction by, so let's use the quotient rule. F prime of x is equal to ln of x prime multiplied by e to the x as is minus ln of x multiplied by e to the x. Literally, you just want to do the quotient rule. So e to the x prime. I'm literally just plugging into the quotient rule, divided by e to the x squared. Okay. Let's see what we can do now. Let's compute each of the primes. F prime of x and plug them in. So for the first one, you got to tell me what ln of x prime. We have to say what ln of x prime is. That's 1 over x. 1 over x times e to the x minus ln of x. Let me just get rid of that thing. So 1 over x times e to the x minus ln of x as is. We didn't put a prime on that one, so that gets copied over as is. What's the derivative of e to the x? That's e to the x as is, divided by e to the x squared. Let me actually show you something that we can do here. We can stop here, but let me show you something good to do. In general, it's good practice to simplify whenever possible. We can take the numerator and factor out the common factor, that's e to the x. In this case, e to the x is a common factor here and here. So let's actually do f prime of x equals e to the x times 1 over x minus ln of x. I literally just factored out the e to the x. It's just distributive property from algebra. I didn't do any calculus with that. Divided by e to the x squared. I can reduce this x and kill it with one of these and be left with just e to the x. So I do believe a good final answer, a very good final answer, post-simplification, is 1 over x minus ln of x divided by e to the x, like so. Let's actually do that. And that seems like a good place to stop for this part of the problem. Okay, the next part of this problem is an important one. It shows you how to do the chain rule with multiple layers. So in this case, what we have is a generalized log derivative. Instead of a clean ln of x, which is easy, the derivative of that would just be a clean reciprocal 1 over x, we have ln of a function. So let's see how we can do this kind of peeling off this layers and this kind of peeling an onion kind of chain rule problem. So this is what you would call a generalized log derivative. This is probably the most challenging problem we'll do today. So generalized log, or I should say ln derivative, in parentheses, chain rule plus log. Good. Good. What am I going to do? I'm going to do f prime of x is equal to, now if you'll recall, the function is ln of whatever is inside. So call what's inside, I don't know what I'm going to call it. I'm just going to call it level 2 or level 1. So what I'm going to do now is I'm going to take the reciprocal, because when I take the derivative of a log, I take the reciprocal of what's inside, 1 over level 1 times level 1 prime. But what is level 1? Level 1 is ln of x squared plus 1. Level 1 is equal to ln of x squared plus 1. So, level 1 prime would just be ln of x squared plus 1 prime. Good. Now, how do we actually compute this? So, in effect, if we plug in, we get 1 over ln of x squared plus 1 multiplied by ln of x squared plus 1 prime. Good. The only part that remains is to compute the prime. Remember, our final answer when computing derivatives must not involve primes. Anything attached to a prime must be resolved first and plugged in. So we have to compute the ln of x squared plus 1 prime. It just remains to compute ln of x squared plus 1 prime. Good. Let's call this, for instance, number 1. Let's call this equation number 1. Then I will just need to find level 2, which is what I'm doing right now. This is what you would call level 2, and I'm plugging back into the equation 1 to get our final answer for f prime of x, which is this little guy. Okay. So, how do we do this? Again, this is another generalized log derivative. Remember, ln is just a natural log. It's still a log. You can refer to it as a log. So in parentheses, chain rule plus log plus ln, or log, or whatever you want to call it. As long as you're not ambiguous, it's perfectly fine. So log is chain rule plus ln, or log, is pretty unambiguous in this case. So what we want to do is, we know that ln of x squared plus 1 prime is going to be what? 1 over what's inside, so 1 over x squared plus 1, multiplied by the derivative of x squared plus 1 prime, like that. Literally, the derivative of ln of something is 1 over that something, the flipped over version, multiplied by x squared, by what's inside prime. So in this case, I literally took this little guy, the x squared plus 1, flipped it on its back, and multiplied by its derivative, this little guy. That's basically the idea. Now, let's actually make sure that we have no primes left. Again, when you're computing derivatives, you don't want to leave a prime. You want to leave a final answer with x's and numbers. You do not, or exponentials and logs. You do not want to have an answer with a prime. That's an incomplete answer. So what is the derivative of x squared plus 1? Well, I do believe that's just the power rule. That's just the power rule. 1 over x squared multiplied by what? What's the derivative of x squared? It's 2x. Plus, what's the derivative of 1? It's just 0, because it's just a number. So, just the 0. Well, I mean, we might as well not write out the 0. It doesn't contribute anything. So, we have 1 over x squared times 2x, in which case we can make it a big fraction and call it 2x over x squared plus 1. Okay, so we have indeed found that ln of x squared plus 1 prime is actually equal to 2x divided by x squared plus 1. That is equation number 2. Now, equation number 1, which is what we want, equation number 1 is f prime of x. Equation number 1 says that f prime of x is equal to this little guy, 1 over ln of x squared plus 1, multiplied by ln of x squared plus 1 prime. We have already computed the ln of x squared plus 1 prime in equation 2, and we just need to plug into that. So plug 2 into 1, and obtain f prime of x. This f prime of x is not a foreign entity. It's actually literally the left-hand side, the far left-hand side of this equation. This equation 1 says f prime of x is equal to this little guy. So this little guy only has one missing ingredient, which is the prime of ln of x squared plus 1. So in this case, that's literally what I'm plugging in for equation 2. 1 over ln of x squared plus 1 multiplied by 2x divided by x squared plus 1. And that seems like a good final answer to put in a box. It doesn't get more simplified than that. Okay, and last but not least is problem 9, part G. Compute the derivative of this function, f of x is equal to e to the x plus ln of x plus x cubed to the power of 3. This is what you would call the generalized power rule. Generalized power rule. And what I mean by this is I don't have a clean x to the power of 3. This is the outer power. I do not have a clean x to the power of 3. That would be too easy. That would be a pure power. That would be an immediate application of the power rule. What I mean by generalized power rule, aka chain rule plus power rule, what I mean by this is nothing but the fact that I have a function, or a more complicated expression involving functions of x, all raised to the power 3. So what I'm going to be doing is I'm going to be taking f prime of x. I am literally going to take the power rule on the outermost power, this one. I'm literally going to yank the power 3 times e to the x plus ln of x plus x cubed. Literally what's inside this guy gets copied over as is verbatim to the power of this little guy minus 3. Remember? You need to knock one off, shave one off the power when you do the power rule. And that is multiplied by the inner derivative, the derivative of what's inside the parentheses, so e to the x plus ln of x plus x cubed prime. Good. Now, what do we have here? We have 3 minus 1, that's 2. So we have f prime of x is equal to 3 times e to the x plus ln of x plus x cubed to the power of 2, multiplied by the derivative of e to the x plus ln of x plus x cubed, all of that prime. Now, the only thing we got to worry about now, remember, we must not leave a final answer in terms of prime. We must clean out all the primes, explicitly compute and substitute them. This, if you will recall, is the building block, is the sum of 3 little building blocks. It's the sum of e to the x plus ln of x plus x cubed. So the derivative would actually be simple. Let's actually do it right here. F prime of x is equal to 3 times e to the x plus ln of x plus x cubed to the power of 2, multiplied by, what do we got to multiply by? The derivative of the building block 1. So what's the derivative of e to the x? It's e to the x formula. What's the derivative of ln of x? What's the derivative of that? It's 1 over x. That's a clean ln of x, not ln of something complicated. Derivative of clean ln of x is 1 over x. What's the derivative of x cubed? It's the power rule 3x squared. So the final answer is going to be the following. F prime of x. This is not something you want to try to simplify on an exam. This would be inhuman, and on any exam I will explicitly state, do not try to simplify your answer. This is more than enough to get you full credit. This seems like a good place to put a box around our obtained answer and stop. Okay, everyone, that concludes, this concludes the worksheet 4 and the plus continuity, so it's kind of a merger, a bit of worksheet 3 continuity only, plus the worksheet 4 rules of derivatives video. Please feel free to reach out if you need any help, if you want to meet on Zoom, or if you need anything, and maybe it can be resolved by email, but I'm happy to meet you on Zoom. As always, you're always welcome in my Zoom room and in my office. Please try your best to attend office hours if you have questions, or send me an email. Best of luck. Thank you as always for watching, and I look forward to seeing you in class or in the office soon. Take care, and thank you so much.